Now we asked the question, are there things that are buried in ice too? We said sea level went up and down because we were moving water from the ocean as snow onto land, and we were accumulating it and compressing it and making it into glaciers which stayed there forever, and when they melted all the water came back and sea level rose again, and as things went up and down people moved into the bottom of the ocean and had to move out or die away, and animals got trapped, ships got trapped, and of course many things came from land through the rivers and so on, and they all got trapped at the bottom, and we can go and dig them up and find things from the past. But now the key question is, as we are moving water onto land and snowing and accumulating snow and compressing it, are there things trapped in the ice as well? Of course there are. What are they? We already mentioned them, about tiny bubbles and so on and so forth. So here is a nice illustration of the few penguins and people drilling holes, and the penguin is saying, hey, what are you doing in my backyard, and so on and so forth, right? So let's imagine that it's snowing in Antarctica, fluffy snowflakes come fluttering down now, not very far from the South Pole. Antarctica is way in the south. Every year another thin layer is added to the snow, and it gets compressed with more and more snow on top. It keeps getting smaller and thinner and so on. So the snowflakes end up lying deeper and deeper under other layers of snow that keeps falling on top. But in the meantime, tiny bubbles of air in the snow are sealed off from outside world. Snow is fluffy, right? So when it falls, it's got a lot of air bubbles inside. It also has dust coming in, pollen coming in, CO2 of course, but also black carbon and all the other things that are getting trapped. So the snowflakes end up lying deeper and deeper under the other layers of snow. Tiny little bubbles of air in the snow are sealed off from the outside world. These bubbles contain, of course, what's in the air: oxygen, nitrogen, and the breath of a mammoth. Think of CO2, a pinch of salt from the sea, because the snow is coming from water evaporating from the ocean, and sea salt is getting carried with it. Many tons, billions, maybe a trillion ton of salt is getting thrown into the air every day because of winds and evaporation and so on. So if you live near the coast, for example, you may know that everything gets salty after a while because the sea breeze is constantly bringing salt along with it, right? So they contain all these things, and they contain pollen and of course CO2, which is what we are talking a lot about here. So year after year, those bubbles find themselves lying deeper and deeper under the snow. Snow falls in thick layers, compressing the snow below and turning it into ice. We keep saying ice, but remember, there is a glacier and there is ice. If you take ice out of the fridge with the permission of your parents and you try to break it or eat it, it's crunchy and it's brittle, whereas glacier flows like molasses. So you have to always remember that, even though we keep saying ice. In every layer, air bubbles become trapped in the ice, and these air bubbles they form the memory of the climate of that time when the bubble got trapped. So if you take out an ice core by drilling a hole in the glacier like this and pull it out, and you can look at how many layers there are and how old the layer is, and then find the bubble at that time of the past, and you measure the CO2, and then you can say, well, CO2 has been changing like this over this period. 800,000 years later, a team of researchers, all wrapped in warm clothes, are standing beside an installation made of poles and cables to bring power. Wind is raw because it's very windy near the the cold North Pole and the South Pole, the temperature is minus 40 degrees Celsius. Attached to the installation is a drill with a diameter of only 10 centimeters, one at a time. Rods of ice are brought up to the surface. You drill a pipe in and pull it out, and you get a rod of ice or glacier, which the researchers then carefully pack, make sure it doesn't melt, and take it away and store it on the ice for some time, and then they bring it to a lab on land in Ohio, in Goa, and elsewhere where there are ice core labs. These are called ice cores. They cut them into 1 meter sections and write on a label what depth this ice came from. The work continues like this for 5 years. The drill goes deeper than 3 kilometers. That's the depth of the ice that was created over this 800,000 years ago in Antarctica, with the bubbles of air trapped inside all this time. It's a nice place called Vostok, which is really, really cold. The rods of ice go to a laboratory with a temperature of minus 35 degrees Celsius. You have a core lab which has to be as cold as Antarctica so that the cores don't melt. So when you go in the lab, you still need to dress up like you are going to Antarctica. It's really fun. Go and visit such a lab. It'll be fun. There are metal tubes on the shelves in the ice cold lab, the core lab, containing rods that have been brought to the surface in different places in Greenland and in Antarctica. And sometimes the scientists take one of these bubbles out of the shelves very carefully. They study the layers of the ice. They melt little bits, releasing the air bubble for the first time in hundreds of thousands of years since it got trapped there. They capture this air in test tubes, and then the analysis begins. They have fancy things like the spectrometer, the mass spectrometer, which measures all kinds of things. The scientists then obtain a wealth of information from the rods of ice. Differences between the summer snow and the winter snow make it possible to tell the year apart by looking at the layers. There are many details. We are being, just kind of simple enough to understand. The grains of pollen in the ice bubbles show which plants were in bloom at that time. Remember, the vegetation has not been the same for 800,000 years. It has changed as the winds change, the amount of rainfall changes, the vegetation changes because of temperatures and the ice cover and the ice retreat and so on and so forth. All that information is buried in there. It's nice detective work. Okay, so if there is a lot of salt in the bubbles of air, there was a lot of wind coming off the sea that year. Remains of ash from volcanic eruptions tell you volcanoes were active at that layer at that time. But the most important factor for us is the temperature, and the other factor that is important for us is the amount of CO2. So we can see if in the past also CO2 has been corresponding to temperature change. Right now we are saying we are burning fossil fuels, we are increasing CO2, and CO2 is a greenhouse gas and it's making the temperatures warmer. If we go back and look at the air bubbles in the ice, is this still true in the past as well? Because that tells you that Earth's climate has always depended on CO2 through temperature and then humidity, then rainfall, then snowfall, and so on and so forth. And here is a nice schematic or the illustration of an ice core. Let's say this is 1 meter long and it's got some various things. There are even little calcareous shells, little shells in the ocean that form calcium carbonate shells and silica shells and so on, and they stay there in the cold, and you can count them and say if they were larger in number and smaller in number. That tells you something about the ocean temperature as well. And there are bubbles with different types of isotopes of oxygen and carbon and pollen and so on and so forth. So you can measure the amount of CO2 in the air in the same way as Keeling did. The temperature in the past is trickier to find out. That has not been preserved in the ice. The thickness of the layers of snow does give us an idea of the temperature. Just like tree rings, when it's very cold, less snow falls than when it's just a little bit cold, because the heat is required to make water evaporate and form clouds from which snow falls, right? So thin layers of snow indicate colder time than the thick layers of snow, but it's possible to be even more precise than that. Already you are learning a lot if you are able to remember that when the air is warmer, it is thirstier, so it wants more water vapor, which comes from evaporation of the oceans and other lakes and so on, and even the moisture in the soil, and then it forms clouds and it falls as snow and rain. And if the air is drier, it holds less water because it's not as thirsty. Think of yourself, if it's hot and humid, you want to drink more water and stay hydrated. If it's cold, maybe you don't feel like drinking so much water, although you should make sure you are always hydrated, right? So you can tell by the kind of oxygen in the bubbles of air if it was cold or warm on Earth at that time. Some particles of oxygen are a little lighter than others, so not all oxygen is oxygen. If you learned chemistry, you've been told O2 atomic number, mass number 16, but there are some oxygen molecules that have more neutrons than protons. So number of protons still makes it an oxygen molecule, but neutrons make it heavier or lighter depending on if there are more neutrons or fewer neutrons than the normal oxygen. So water with light oxygen particles evaporates more quickly because it's lighter, and the air can pick it up wind can pick it up easier. When it's colder, it's more difficult for water to evaporate, so it is mainly made up of light oxygen particles because heavy oxygen particles are not being picked up when there is less wind and less warm temperatures and less evaporation and so on. So it's mainly light oxygen particles that find their way into the clouds and the snow when it's colder. So if you find layers of ice with bubbles of air in them with lots of light oxygen particles and not many heavy oxygen particles, remember snow is H2O. So you are talking about H2O with the O that is heavier or lighter. It turns out that hydrogen also has different versions of itself. So it's a bit complicated, but just try to understand as much as you can that scientists have many clues from the past with which they can do detective work to find out past temperatures, past oxygen, past vegetation, and so on. Luckily, we can leave this sort of research to the experts. They could tell from the ice that for 800,000 years, that's the longest ice core we have got from Antarctica. From 800,000 years, there was never more CO2 in the air than 278 particles per million. Where did 278 come from? When the last ice age ended about 10,000 years ago, we ended up with 278 ppm in the air. Now we are at over 420. We have increased it quite a bit, and that's more than anything we have seen in 800,000 years, as we can learn from the ice core from Antarctica. So it's quite remarkable that we now suddenly have more than 400 particles per million in the air. If you combine the increase in temperatures and the increase in CO2 in a graph, you will see that they follow almost exactly the same pattern. If the CO2 rises, then the temperature rises, and if the temperature rises, then CO2 rises further because you keep melting the ice, and ice which has put the CO2 buried and capped in the ocean and so on begins to bubble out all over the place. So we'll come back and look at this nice graph in the next podcast, because this is a bit complicated, but it's fascinating. It's very interesting. It goes from 800,000 years ago forward to the present time, and you can see that CO2, which started at about 278 after the end of the last ice age has now shot up over 400 ppm. We'll come back and learn that. Just try to make sure you understand the concepts, because these are complicated, but if you listen carefully, maybe you'll understand enough. If you're too young, don't worry, just listen to it now and come back later, few years later, and say, haha, now I understand it. Okay, we'll come back and look at this graph of temperature and CO2 from Antarctic ice core for 800,000 years. Come back quickly, okay?